So we've talked about shear stress, and we talked about viscosity and the no slip condition, and a little about boundary layers. So now let's talk about the last part of that equation, and that's the strain rate, and that is your du dy. Okay. So let's say we have a fast moving bus. Okay, so a fast moving bus is going to have a velocity profile that looks something like this. It still has to be 0 at the wall, at the bus's surface. And out away from the bus, you're going to have a great big velocity. So a big long arrow for a fast moving bus. Okay, let's say on the other hand we have a slow moving bus. So this is our y direction. So a slow moving bus, same thing is again, we're talking about a bus sitting in a wind tunnel and the wind blowing over it. It's the same thing as the bus moving. So here's a slow moving bus, or a slow airflow over a bus. So out here far away from the bus, we're going to have the air velocity, the same thing that we had out in front of the bus. Okay, so our velocity profile is going to be something more like this. Still 0 at the bus surface, it's just not going to end up as big. Okay, our strain rate, see it's a derivative, and a derivative is a slope. So our strain rate again, du dy, is what we're talking about here. Okay, so this is going to be a little bit weird for you because we have, in calculus, you always did dy dx. But here we got kind of like dx dy. Okay, so everything is going to be an opposite world here from what you had in calculus. So if we're going to look at which one of these has a large strain rate and where is the strain rate higher, our slopes are not going to look the same as they did in calculus. So you have to think about it a little bit differently. Okay, so remember our whole equation though was tau equals mu du dy. Alright, so a higher viscosity, that was our mu, means that it's going to take more shear stress to get the same strain rate. Okay, so it's easier then to move through a high viscosity fluid. So let's think about that strain rate again, and that velocity gradient, and how it is backwards from what we had in calculus. So when you look at a slope, it's not going to look the same way it did in calculus, and the slope is the strain rate. Okay, but in order to think about where is the strain rate highest, and which case the fast or slow bus has the higher strain rate, let's think about, well, what is a du dy? A du dy is just a delta u, or a delta velocity, over a delta y, or a distance, taken to the limits, right? So infinitesimally small du dy, or infinitesimally small dy, really, delta y. Okay, so instead, let's not think of it in the limits. Let's think of it as a delta y. So if I put the same delta y on both these pages, so let's make a delta y, say, from here to the bus surface. And I put the same delta y, say, here to the bus surface. Okay, let's figure out now which one of these cases has the bigger slope or the bigger strain rate. Okay, same delta y, so how do you figure out which one has the bigger strain rate? Well, let's look at delta u. So delta y, the denominator is the same. Which one has the higher delta u? Higher delta u in, well, look at this. This delta u, it's 0 here, it's big here. 0 here, not so big here. So higher delta u in the fast bus case. Okay, and if you think about in calculus, when you always had dy dx, it doesn't look like a higher slope, right? But it is. Okay. The other thing we want to do is look at where is that slope, or where is that strain rate highest. Near the bus or far away from the bus? Okay, so if this was calculus, here you'd have an infinite slope up out here, but this is not calculus. This is backwards calculus, right? So if you look at this delta y, okay, from here to here, let's put a same delta y out here. Okay, does this area have a bigger delta u, or this area have a bigger delta u? I'm thinking this area down near the bus has a bigger delta u, and if you get far away from the bus, there's not going to be any delta u at all, right? The velocity won't be changing at all. So we are going to find the highest strain rate at the bus surface. Okay. And again, it looks a little backwards from what you had in calculus, but that's just because your axes are backwards. Okay, so let's do an example. So again, our equation was tau equals mu du dy. Okay, so let's say we have a velocity as a function of y. So we have that velocity profile. What we're going to do is take its derivative, we're going to multiply it by viscosity mu, and then we'll have our shear stress tau. Okay, if we want to have shear stress at the wall, now plug in y wherever the wall is, and you have your answer for shear stress. Usually, again, though, we're looking for, say, a force or a moment. If it's a force and shear stress is constant, you just multiply it by a to get the total force. If it's a moment, then you say the moment is going to be that force times some distance, say r, which is tau, the wall, a times r. Okay. So let's do a little example. This time we're not going to find force, we're just going to find the shear stress at the interface of the sand. So what this is wind flowing over a beach, and we're given the velocity profile. So here, close to the beach, we have this u times sine pi y over 2 delta. That is our equation for u. Outside of this delta, okay, so this delta is actually our boundary layer. Outside of the boundary layer, the velocity is not changing, it's all just u, the wind velocity. Okay, the reason it's 0 here at the wall is because of that no slip condition. Okay, so let's find tau at the sand interface. All we have to do is apply our equation. Tau wall is mu times du dy at, and in this case our wall or our sand surface is at y equals 0. Alright, here's y, so y equals 0, that's where we're looking for it. Y equals 0. Okay, so the first thing we need is that derivative. So at y equals 0, we're not out here outside the boundary layer, we are in the boundary layer, so we need to use this equation. So our du dy, just take the derivative, and don't get derivatives and integrals mixed up. It's a common mistake to try to integrate instead of take the derivative. We're going to use the chain rule, and it's going to come out to u, big U, that was just a constant, times pi over 2 delta times cosine pi y over 2 delta. Okay, so now let's plug in y equals 0 and du dy at y equals 0. Well, you plug in a 0 here, cosine 0 is just 1, so that's u times pi over 2 delta. Okay, so our tau at the wall, or tau at the sand, at the beach air interface is just going to be mu times du dy at y equals 0, which is just going to be mu times u times pi over 2 delta. And that's our answer. Okay. Be careful. Don't try to plug in y to this equation. Don't plug in y equals 0 to this original equation, because that would make the derivative 0 when it really isn't 0. Just because u is 0 doesn't mean its derivative is 0 there. So you got to take the derivative first. Few notes on the strain rate and this particular problem. Notice that tau, if you could calculate not just at y equals 0, but plugging in this equation, it's going to change as we go out. It's going to be maximum at the wall. Okay. We can see how it varies by looking at how u is changing. And where u is changing the most, you're going to get the highest strain rate and therefore the highest shear stress as well. Okay. So, and again, tau at the wall at the air-sand interface was mu du dy at y equals 0. That's the wall shear stress. And where that velocity was changing, close to the sand, that's the boundary layer. That delta is called the boundary layer thickness. Okay? And that's basically where the sand is influencing the airflow. Further away outside the boundary layer, the air doesn't even know that the sand is there. Okay. So here we were given, for this example, we were given a velocity profile. A lot of times that's the hard thing to find, and we will have other methods in order to find velocity profiles. All right, so that's all I've got. You can go ahead and finish the quiz, and I will see you in class.